Hello, I'm Patty Simpson with Simpson Math. Let's talk about probability. We see probability every day in our lives. We may not realize it, but we're dealing with that probability all the time. In fact, you'll see probability in the cost of different things, like your insurance, your car insurance, or your house insurance. When you buy a car or when you buy a house, your interest rate that you get from the bank is dependent upon probability. And in science every day in our lives and how doctors treat us and the different medicines we take is all based upon probability. So whether we know it or not, we're dealing with probability all the time. Your car insurance, where you live, helps to determine that cost, because if you live in Podunk, Texas, where there's no cars around, it's less likely then that you're going to be in an accident than if you live in a big city like Houston or Dallas. So you're going to pay more for your car insurance in a place like Houston or Dallas than you might in Podunk, Texas. So, and then also your age group. So like I have 2 teenage boys. My insurance is going to cost a lot because it's more likely that a teenage boy has an accident than an old lady. So your age and your gender makes a difference in how much you're paying for your car insurance. And all that's based upon probability. So you may not know it, but you're dealing with that probability all the time. And we're going to be learning about probability here for a bit. Let me give you an example of a place where we saw probability fit into our everyday lives. So we had a life insurance on my mom for $10,000. And when my mom died, the insurance company gave my dad an option. They said, look, you can have a one-time payment of just $10,000, or instead what we'll do is we'll pay you $275 for the rest, a month, for the rest of your life. So we had to stop and think about, why was the insurance doing that? What is it that is making them want to give him $275 for the rest of his life every month rather than the $10,000? And then we had to make a decision on which we were going to do. So let's just look and see, when we were making our decision, why is it that the insurance company was wanting to give that $275 a month as compared to that $10,000 lump sum? So we looked at it and we saw how long would it take him to make $10,000. Well, if we did $275 a month for 10 months, he would make $2,750. Well, to make it to a year, then we need 2 more months. So then we said, well, let's do 2 more months of that. So do 2 more months of that, get $10, 10, 14, 15, carry 1, 4, 5. So $550. So if you want a full year, $275 for 10 months plus $550 for 2 months gives us 1 full year. So after a year, he would get a payment of $3,300. Well, so that means if I do that for 3 years, after 3 years, he would have $9,900. So after 3 years and a month, my dad would start making more than that $10,000. So we started asking ourselves, why do they want to give him a potential more than $10,000? Why would they give him that $275 a month? So we looked into it, and it turns out that if your spouse dies, that the probability that you die then within 3 years is really high. And if you think about it, it makes sense, because most of the time when your spouse dies, you're older. And so therefore you're probably on the verge of death yourself. And so it would totally make sense then that within that 3 years, my dad would die as well. So us understanding probability completely, we decided that Dad wasn't going to make it 3 more years, and instead of taking the $275 a month for the rest of his life, we went ahead and took the straight up payment of $10,000, help pay for funeral costs and whatnot. Turns out the dad's lived more than 3 years. He beat the odds. Who knew? So we could have made some money off of it. But using that probability that he should have died within 3 years, we just took that lump sum. So those are types of decisions, though, that insurance companies and people have to make all the time based upon probability. So we're going to spend a little bit of time learning about probability. Let's look at the characteristics of probability. So first, the probability is just the extent to which an event is likely to occur. It's how likely is something is to occur. And we measure it by a ratio, a fraction of the favorable cases to the number of total cases that there are. So let me give you an example. Here I have a bag of Skittles. If I open that bag and I see how many Skittles are in my bag, well, I have 2, 3, 4 red Skittles. I have 2 yellow Skittles. I have 2 orange Skittles. I have 3 green Skittles, and I have 1 purple Skittles in my bag. And I want to know if they're in the bag and I just randomly pour one out, what is the probability that I'm going to get out a green one? So, you know, if these are in the bag and then I shake them up, and then randomly just choose one out, what's the probability that that one is a green? And the way we find that probability is we create this ratio of favorable cases, in this case a green, to the total number of cases. So a little bit of notation about probability. When we talk about probability, we use a P, and then we put inside our parentheses whatever it is that our favorable case is. So in this case, my favorable case is a green. Some people will write it as X equals green because the color is your variable, or we could just write it with just the probability of green. Then to find that probability, we take the number of favorable cases. In this case, there are 3 favorables, 3 greens, and we put it over the total number that there are. Well, I could just count my Skittles to find out the total number, or I could add them up. 4 plus 2 is 6, plus 2 is 8, plus 3 is 11, plus 1 is 12. So there are 12 total Skittles in my bag. So the probability is 3/12. Or we could reduce that down to 1/4. So that the probability that I get a green is 1 out of every 4 attempts. I would expect to get a green out of my bag. So if I did that again, where I mixed them all up and pulled out a Skittle from my bag, 1 out of 4 attempts of doing it, I would expect to get a green. I can also write that fraction we know as a decimal. So 1/4 is the same as 25 hundredths, or I could write it as a percent out of 100. So think about moving that to the hundredths place, would be times 25 times 25, so it's 25%. All of these are acceptable ratios that show that probability. So 1/4 of the time, or 25 hundredths of the time, or 25%. So a big deal about probability is that our probability is going to be a fraction. One of the characteristics is that probability is a fraction. So that you have a ratio, a part out of the whole. But let's look at this next thing to find out another characteristic of it. What is the probability I get a blue? So if I choose just 1 Skittle out of the bag, how often am I going to get a blue out of my bag? Well, how many blues do I have? There are 0 blues. So the probability that I get a blue, my favorite outcome is blue, is 0 out of the total of 12 Skittles. But 0 divided by 12 is 0. There's not a blue in the bag, so the probability that I get a blue is 0. So if something is not probable, then we say that probability is 0. It can't happen. So when I say probability is a fraction, it's a fraction that includes 0 as well. So my probability it's got to be greater than or equal to 0. So in this case, it's actually equal to 0 because it's not probable. So when your probability is 0, it means it cannot happen. Let's check out this last one. What is the probability I get a Skittle? If I draw out of the bag, what's the probability that I get a Skittle? Well, I'm going to get a Skittle every single time. All 12 of my things in the bag are Skittles. So the probability I get a Skittle, well, there are 12 Skittles in the bag out of a total of 12, which is 1 or 100%. 100% of the time I'm going to get a Skittle. It's a for sure thing. So when our probability is 1, it means it is a for sure thing. So when I say that the probability is a fraction, it's a fraction including 0 and 1. So my probability is going to be it's going to be greater than 0, but less than or equal to 1. And that's going to be true for all of our probabilities. So as you get probability questions, you should always check to make sure that your answer is somewhere between 0 and 1. It can be 0 if it's not likely, if it can't happen at all. And it can be 1 if it for sure will happen. Then your probability can be 0 or 1, or something in between. But if I get something like 3.6 as my answer, I know that something's wrong because my probability should be between 0 and 1. Let's look at the vocabulary around probability. First, let's talk about an experiment or a trial. An experiment is any process with the result determined by chance. So maybe if I'm looking to randomly choose a Skittle from a bag of Skittles, then my experiment is drawing a Skittle from the bag. The experiment could also be something like rolling a dice or drawing a card. And sometimes an experiment just happens also every day in life. Things like when you get into a car to drive your car, that's an experiment in itself. What's the outcome? Well, the outcome of that might be determined by chance. So a probability experiment is just something that the outcome of it is determined by chance. Then an outcome is each individual result that's possible for the probability experiment. So I could draw a green. Green is an outcome of this experiment. As I draw from a deck of cards, I could draw an ace. An ace is an outcome from drawing from a deck of cards. I could be in a wreck for driving my car. Being in a wreck is an outcome for that experiment. So each one of them is an outcome. So each one of these guys is an outcome. Sample space is the set of all the possible outcomes. So in this case, I could draw a red, yellow, an orange, a green, or a purple. So the sample space is the set of all of those possible outcomes. So the sample space is just the set of every single possible outcome that can happen in the experiment. And a symmetric sample space, or an equally likely sample space, is the set of all possible equally likely outcomes. In my example here with the Skittles, it is more likely that I'm going to get a red because there's more reds than there are purples. So it's more likely I'm going to draw a red than a purple. So in order for me to have the symmetric sample space, each one of these must be equally likely. It's just as likely as I pull this red as it is this yellow. Whereas over here, that was more likely. Drawing reds is more likely than yellow because there are 4 reds in the bag. But here, by putting each one of them individually, it's just as likely that I pull this red as it is that I pull that red, as it is that I pull this orange, as it is that I pull the one purple. So now this is the set of equally likely outcomes. Each one of them is just as likely. And an event is the subset from the sample space. Earlier we called this the favorable outcome, the thing that we're looking for. So an event is just part of your sample space. So for instance, if I'm finding the probability of red, then red is my event. If I'm looking for the probability of red or orange, then red or orange is my event. If I'm looking for the probability I get a Skittle, then Skittle is the event. So the event is just something, a subset, part of my sample space. Let's look at sample spaces and symmetric sample spaces. First, we have an experiment where we roll a 6-sided die. Let's create just the sample space of that experiment. Remember, a sample space is just the set of all outcomes that are possible from the experiment. So if I roll a 6-sided die, I could roll a 1, I could roll a 2, I could roll a 3, I could roll a 4, I could roll a 5, and I could roll a 6. So the sample space of rolling a 6-sided die is 1, 2, 3, 4, 5, 6. Those are all the possible outcomes. Now we ask ourselves, is each one of those equally likely? Is each one of them have the same probability as the next? And it's just as likely as I roll a 1 as I roll a 6. Each one of them just shows up one time on my 6-sided die. So therefore my symmetric sample space looks exactly the same. 1, 2, 3, 4, 5, 6, because each one of these outcomes is equally likely. So in this case, for this experiment, my sample space and my symmetric sample space are identical. Let's look at the experiment of tossing a coin and rolling a 6-sided die. In this case, I'm going to toss a coin, and it could land on heads or tails, and then I'm going to roll that 6-sided die, and where I could get a 1, 2, 3, 4, 5, or 6. So what are the possible outcomes? Well, it might be easier to draw a tree for these two. And so on the coin, I could get a heads or a tails. I'm going to draw a sideways tree because I don't have a lot of space here, but I could get a heads or a tails. Those are my two outcomes for tossing a coin. Then I'm going to roll a 6-sided die. So if I got a heads on my coins, I could get a 1 on the die. If I got a heads on the coin, I could get a 2, or I could get a 3, or I could get a 4, or I could get a 5, or I could get a 6. So there are 6 different possibilities that I could get if I get a heads first. I could get a heads and a 1, a heads and a 2, a heads and a 3, a heads and a 4, a heads and a 5, a heads and a 6. What about if I get a tails first? Well, if I flip the tails first, I could still get those same possibilities on my dice, where I'm getting a 1, a 2, a 3, a 4, a 5, or a 6. So there are 6 possibilities for if I flip the tails as well. A tails and a 1, a tails and a 2, tails and a 3, tails and a 4, tails and a 5, and tails and a 6. These are all the possible outcomes for this experiment of tossing a coin and then rolling a 6-sided die. So this is my sample space. Now let's look and see if each one of those is equally likely. Each one of those shows up exactly one time, so it's just as likely that I get a heads and a 2 that I get a tails and a 2. Each one of them has the same likelihood. And so this is both my sample space and it is my equally likely sample space as well, my symmetric sample space as well. Let's look at if I have 3 children. I decide I want to have 3 children. What are my possible outcomes? Well, let's just look at the sample space for a second. I could have, if we think about my options, I could have all 3 boys. So 3 boys is one possibility. Another possibility is to have all girls. So I could have 3 girls. Maybe I just have 1 boy and 2 girls. So another possibility is 1 boy and 2 girls. And then the last possibility is 1 girl and 2 boys. So I could have 1 girl and 2 boys. So I could have 0 boys, 1 boy, 2 boys, or 3 boys. So those are my possible outcomes, my sample space. Is it equally likely that I have 3 boys? Is it just as likely I have 3 boys as I have 3 girls? Do those have the same probability? Well, we can make a tree diagram to help us see. If, like here, they each show up one time, then we will know that they are equally likely. So let's make a tree diagram to show those outcomes. So here, the first child that we have, on the first child, I could have a boy or a girl. So I'm going to show that using this tree diagram, that I could have a boy or I could have a girl. Now, on my second child, if I had a boy on the first one, then on the second one, I could have a boy, so that I have a boy and a boy. Or if I had a boy on the first one, I could have a girl on the second child, so that I have a boy and then a girl. Well, what about if I have a girl first? Well, if I have a girl first, then I could have a boy next, so that I had a girl and then a boy. Or I could have a girl and then a girl. So this is all the outcomes for if I have two children. I could have a boy and a boy and a girl and a boy, or a girl and a girl. Those are 4 different outcomes there for having 2 children. Then what about on the third child? Well, here I have a boy. So here I had 2 boys. Well, on the third kid then, I could have either another boy, so that I end up with 3 boys, or I could end up with a girl. So what have I had? Well, I had a boy and then a boy and then a boy. A boy and then a boy and then a boy. Or I could have had a boy and then a boy and then a girl. Boy and then a boy and then a girl. Here I had a boy and then a girl. So what could happen on that third kid? Well, I could have a boy or I could have a girl. So in this case, if I had a boy first and then a girl, then I ended up with a boy, girl, boy. Here I ended up with a boy, girl, girl. Now, that's all my potentials for if I have a boy first. But what if I had a girl first? Well, I could have had a girl and then a boy, in which case, then I could have a boy or I could have a girl. So another option is to have a girl, a boy, or to have a girl, a boy, and then a girl. And then last but not least, I could have a girl. Well, if I have a girl and then a girl, I could end up with a boy, or I could have all three girls. So a girl, a boy, or a girl, a girl. So now let's look and see, is it equally likely that I have all boys? Does that have the same likelihood as having one boy and two girls? So let's look and see, one boy and two girls, how many times does that show up? Notice that turns up actually 3 different times. So it's more likely that I end up with one boy and two girls. That's more likely than for me to have 3 boys. It's more likely that I'm going to have one girl and 2 boys. That's more likely than me having all 3 girls, because there's only one way for me to have 3 girls. So this is my sample space, but it's not my symmetric sample space because they're not equally likely. In order for it to be an equally likely sample space, I would have to show all the different outcomes here, so that this whole thing is my symmetric sample space. All of those are equally likely now. Now it's just as likely I have a boy, a boy, a boy. That's just as likely as me having a boy and then a boy and then a girl. That's just as likely as me having a boy and then a girl and then a boy. So this is my symmetric sample space, or my equally likely sample space. Now, symmetric sample spaces are really important to find, because it turns out that probability and area are related. So if we can find this symmetric sample space, it really helps us to be able to see or find the probability of different experiments. Let's find the probability for the experiment of having 3 children. So earlier we found the sample space and the symmetric sample space for having 3 children. And we saw that the sample space and the symmetric sample space were not the same thing. When we find probabilities, we need to make sure that we are using our symmetric sample space to find those probabilities. So we're going to use the symmetric sample space that we found earlier to help us find the probability. So what is the probability that we have 2 boys and 1 girl? I'm going to write that in the notation that we use for probability, where I say the probability that we have 2 boys and 1 girl. Remember that with probability, that's a ratio of our event out of our total number of outcomes. So the first thing I'm going to look for is the number of ways that we can have 2 boys and 1 girl. And I'm going to look here where it's equally likely those outcomes, not at my sample space. If I look at my sample space, it looks like it's 2 out of 4 possibilities. But if we look at our symmetric sample space, we see there are actually 1, 2, 3, 4, 5, 6, 7, 8 different ways that we can have 3 kids. That's the total number of outcomes is 8. So that 8 is going to be my denominator. Then I'm looking for the number of ways that I can have 2 boys. So how can I have 2 boys? Well, I can have 2 boys here, a boy and then a boy and then a girl. Or I could have a boy and then a girl and then a boy. Or I could have a girl and then a boy and then a boy. And those are the 3 ways that I can have 2 boys. So there are 3 out of the possible outcomes where I can have 2 boys. What's the probability that we have 3 girls? So again, in that notation we use for probability, we have 3 girls. Or I could say that as 0 boys. That's the same thing as having 3 girls. In our sample space, I wrote it that way, as 0 boys. That's the same thing as having 3 girls. Well, there's only 1 out of the 8 possibilities where we have no boys. So the probability that we have 0 boys is 1 out of my 8. So we see that the probability of having 0 boys is not the same as having not the same as the probability of having 2 boys. And using the symmetric sample space helps us to find that probability. So being able to find your symmetric sample space is really important in probability. Let's find the probability using a spinner. So here we have a spinner, and we're just going to spin that spinner. So the experiment in this problem is spinning that spinner. The outcome from spinning the spinner is determined by chance. So when an outcome is determined by chance, that process involving that is the experiment. So we're spinning a spinner here. I want to know, what is the sample space? Well, the sample space are all the possible outcomes. So if I spin this spinner, what could happen? Well, I could land on a green, I could land on a red, I could land on a white, or I could land on a blue. The question is it each one of those equally likely? Is it just as likely that I land on a green as I land on a white? Are those the same possibilities, the same probabilities? So the symmetric sample space shows each possibility equally likely. So if I divide this up into equal pieces so that all of my pieces on the spinner are exactly the same, like so, now it is just as likely as I land here as it is that I land there. And we see in that case that green shows up 1, 2, 3, 4 times. So in order for me to write the symmetric sample space, I would need to write that green on here 4 times. So now it's just as likely I land on this piece of green as it is I land on that piece of green. So for my symmetric sample space, I need green 4 times, I need blue 2 times, I need white 1 time, and I need red 1 time. That is my symmetric sample space. Now I'm going to find the probability using this symmetric sample space, and we can really see how probability and area are related. So for instance, on this first one, I want to know the probability that we spin a green. Remember that for probability, it's the number of ways we can get this event over the total number of outcomes. Well, if we look, we see that there are a total of 1, 2, 3, 4, 5, 6, 7, 8 equal pieces, or 8 equally likely outcomes. That 8 is our denominator. Then we look for the total number of ways we can get that event of green, in which case there are 4 of those pieces. So 4 eighths, or 1/2, or 50% is the probability that we spin a green. We can really see that area of our circle is also 1/2. So probability and area are related. If it takes up half the circle, then the probability I hit it is 1/2. Let's look at the blue. The probability I spin a blue on here, well, there are 2 blues out of my total of 8. So 2 eighths is the probability that I spin a blue. Or I could reduce that to 1/4. So if I spin my spinner 4 times, I would expect at least one of those. I would expect 1 time. Theoretically, I would expect 1 time for me to land on blue. Spin it 4 times, I should land on blue once. Also, you see that the circle, 1/4 of this area of this circle is made up of blue. So therefore, the probability that I hit blue is 1/4. Let's look at this not white. What's the probability that I don't get white or I don't land on white? This not white is what we call the complement. I want to know the complement of getting white. So this is equal to the complement of probability of white. And we write that complement in this notation. When I'm talking about the complement, I say the probability of not white. And this just tells me that I'm looking for the complement of white. Some people will write it, or in some books, they'll write it with a C up here, the complement of white. So let's just see what is the complement of white. Well, there's one spot on here of getting a white. That means that there are, if we're not counting white, if we're looking at the ones that are not white, we're looking at the rest of them. So there are 7 that are not white. So the probability is 7 out of 8. Or we could have done it this way. We could have said our whole circle makes up one whole circle. And I'm going to take away my white because I don't want the white, not the white. So I take away the 1/8 that is my white. And that leaves me with, well, 1 could be rewritten as 8 out of 8 minus the 1 out of 8, which is 7/8. So the probability that I get not white is 7 out of the 8 pieces, which we can see again that the area of my circle is 7 out of the 8 pieces are not white. So there's a little bit on finding probability using this spinner. Let's look at the complement. First, remember that the probability of all the possible outcomes of an experiment should add up to be 1. So everything, all the different possibilities should add up to be 1. Here's an example of that. Given the experiment that we're going to have 2 children, find all the outcomes and their probabilities. We looked at this earlier with 3 children. So with 2 children, on the first one, I could have a boy or a girl. And then on the second child, I could have a boy or a girl. Or I could have a boy or a girl. So my outcomes for this are boy, 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 girl, girl, boy, or girl, girl. That's my symmetric sample space. The sample space itself are just, well, I could have 2 boys, I could have just 1 boy, or I could have 0 boys. So let's just look and see the probability of each one of those. The probability I have 2 boys, well, it's 1 out of 4. So I have a 1 out of 4 chance of having 2 boys. The probability I have 1 boy, well, there are 2 ways that I could have 1 boy out of the 4. So 2 out of 4, or 1/2 is my probability that I have 1 boy. The probability that I have 0 boys, well, there's 1 way out of 4 that I can have 0 boys. So 1 out of 4. So these are my different outcomes. My x values are 2, 1, and 0. And the probability that I get that x value here is at 1/2, 2/4, and 1/4. Later, we're going to call what I've just created here a probability distribution, where I've made a distribution that shows all the possible outcomes and their probabilities. Notice that when I add them together, 1/4 plus 2/4 plus 1/4, that adds up to be 4/4 or 1. So your symmetric sample space should always, your probability should always add up to be 1 if you've gotten all the different possibilities and their probabilities. Now the complement, if you're given an event E, like for instance, maybe I want to know the probability that I get 1 boy, which we found was 2/4. The complement is all those outcomes that are not this. So in this case, if it's not one boy, then it's 2 boys and 0 boys would be the complement of that. So the complement of 1 boy, we can write it like that, or I can put this symbol inside, or sometimes people will write a C to let you know that it's the complement. That complement, this says the probability of not 1 boy. And the probability of not 1 boy are the probabilities other than that. So in this case, 2 boys and 0 boys. So that probability would be 1/4 and another 1/4, which makes also 2/4. Consists of, so the complement is just everything else in the sample space that's not this. And there are some certain things that we should know about it. For instance, that the probability of E plus the probability of not E, those 2 probabilities should add up to the entire set. They should add up to be 1. So notice that the probability of 1 boy plus 2 boys and 0 boys makes up the entire sample space. That's what this says. Then the probabilities of each of them add up to be 1. Because of that, if we know one part of it, we can find the other by subtracting. So if I know the probability of an event, I can find its complement by subtracting from 1. And vice versa, if I know its complement, I can find the probability of an event by subtracting from 1. So here's an example of that. Given the experiment of having 2 children, what's the complement of having 2 boys? So the complement of having 2 boys was everything else in the set. So the complement of having 2 boys would be 1 boy and 0 boys. So the complement is 1 boy and 0 boys. Now, if I wanted to know the probability of that complement, then I could say the probability of not 2 boys is equal to 1 whole thing minus, well, the probability of 2 boys is 1/4. So 1 minus 1/4 is equal to 3/4. Or look and notice that 1 boy and 0 boys, sure enough, that 2/4 plus that 1/4 makes 3/4 altogether. So the probability of not 2 boys would be 3/4. So the complement just makes up the rest of the sample space. Let's find the probability of this problem. So my brother and I were trapped on an island, and we each have a 6-sided die that we carry around in our pocket at all times. So we had 2 6-sided die, and we found a banana on the island. So we had these 2 6-sided die and a banana. And we were trying to decide who was going to get to eat the banana. And we decided that what we would do is we'd play a little game where we rolled the 2 6-sided die. And my brother, being the nice guy that he is, said that if we rolled the 2 6-sided die and a 1, 2, 3, or 4 was the larger of the 2 6-sided dies, then I would get the banana. But if a 5 or a 6 was the larger, then he would get the banana. So for instance, if I roll these, in this case, I rolled 2 4s. So I would get the banana because 4 is the largest number. Let me roll it again. And here there's a 2 and a 1. So 2 is the larger number, so I would get the banana. In order for him to get it, there I rolled a 1 and a 6. 6 is the larger of the 2 numbers, then he would get the banana. So that we decided to play this game, and I want to know what's the probability that I get the banana? How much advantage do I have over my brother in this game? So let's find that out. Now we know that the probability, in order to determine that probability, we need to know the number of ways that I would win. In other words, the number of ways that I could get a 1, 2, 3, or 4 as the higher number. And then we need the total number of outcomes. So it's easiest maybe if we find the symmetric sample space to help us. So we're going to find all the different ways that we could roll these dice. Well, as we're rolling the dice, on one die we could roll a 1, a 2, a 3, a 4, a 5, or a 6. On the other die, we could roll the same thing, a 1, a 2, a 3, a 4, a 5, or a 6. I'm going to make a table that shows the symmetric sample space, that shows all the possible things we could roll. So for instance, I could roll a 1 and my brother could roll a 1. I could roll a 1 and my brother could roll a 2. I could roll a 1 and my brother could roll a 3. I could roll a 1 and my brother could roll a 4. I could roll a 1 and my brother could roll a 5. I could roll a 1 and my brother could roll a 6. So those are 6 possible outcomes from this game. Or maybe I roll a 2. Well, if I roll a 2, then my brother could roll a 1, a 2, a 3, a 4, a 5, or a 6. I could roll 3. If I roll a 3, my brother has those same possibilities that he could roll of 1 through 6. If I roll a 4, then again, my brother has those possibilities of 1 through 6. I could roll a 5, and again, my brother has those possibilities of 1 through 6. And then maybe I roll a 6 and he rolls a 1, or I roll a 6 and he rolls a 2. I roll a 6 and he rolls a 3. So this is all the different possibilities of what we could roll. This chart, this table, shows my symmetric sample space, all the different possibilities of what we could roll. Now I want to know the probability that I win. And in order for that to happen, the biggest number has to be a 1, a 2, a 3, or a 4. So I'm going to go through and circle, well, first of all, the probability that I win. We know that the total number is going to be on the bottom. And there are 6 times 6. There's a total of 36 potential outcomes. 36 different outcomes. And I want to see how many outcomes do I win. Well, here I win because 1 is bigger. Here I win because 2 is the biggest. 3 is the biggest. 4 is the biggest. 5 is the biggest there though, so my brother wins. 6 is the biggest there, so he wins. Here, 2 is bigger, I win. 2 is bigger, I win. 3 is bigger, I win. 4 is the biggest, I win. 5 though and 6, my brother wins. 3 is the biggest. 3 is the biggest. 3 is the biggest. 4 is the biggest. 5 is the biggest, my brother wins. 6 is the biggest, my brother wins. 4 is the biggest. 4 is the biggest. 4 is the biggest. 4 is the biggest. 5 and 6 again, my brother wins. 5 is the biggest, 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 and 6 is the biggest. Oh, my brother wins all of those. 6 is the biggest, 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 and 6 is the biggest. Oh, my brother wins all of those as well. So I win, well, 1, 2, 3, 4 times 1, 2, 3, 4. I win 16 out of the 36 times. Or we could reduce that. 4 goes in there 4 times, and 4 goes in there 9 times. So 4 out of 9 times, I'm going to win. Hey, wait a minute. If I'm going to win 4 out of 9 times, what's the complement of that? Or how many times then would my brother win? What's the probability then that my brother wins? My brother wins. Well, if I'm 16 out of 30, the rest of the time he would win. So we could find that complement by saying 1 minus the 16 out of 36, or the 4/9. Well, 1 is 9/9 minus 4/9. So that means the probability he wins is 5/9. He has a better chance of winning. I thought that he was being nice by letting me have 1, 2, 3, or 4, and it turns out that he has a better probability of winning the banana. Luckily, right about then, my other brother showed up in a boat, and we got to leave the island, so it didn't matter anyway. Let's look at the different types of probability. First, let's start with subjective probability. Subjective probability is just an educated guess regarding the chance that an event will occur. So the weatherman, when he predicts the weather, he's basing that on different signs and things in the environment that helps him to make that educated guess. But he's really just giving an educated guess to what the weather is going to be the next day. So when he says it's a 90% chance, that's the probability that he believes that it will rain. Now, I'm going to listen to the weatherman more than I'm going to listen to, say, my brother when he looks out the window and predicts what the weather is, because the weatherman is actually giving some educated guess, like he has some expertise in the matter, and so his prediction is probably going to be more valid than my brother's prediction. Here's another example of that subjective probability. An economist predicts the value of a stock. Again, he's got some sort of measures that he's looking at to help him to make that educated guess. His prediction's probably going to be a lot better. His probability of the value of the stock is probably going to be a lot better than mine is. So because he has that expertise. So subjective probability is just an educated guess. Theoretical probability is the probability in theory, what should happen in theory. But in order for us to be able to tell the theoretical probability, we must be able to find the symmetric sample space for an experiment in order for us to be able to tell what the theoretical probability is. And with the theoretical probability, this is what we've been dealing with here for the last little bit. When we spin the spinner or when we roll a dice, we're able to look at that theoretical probability. But sometimes we can't do that. For instance, when we're dealing with the weather, I can't come up with a symmetric sample space for the outcomes of weather. So I can only use theoretical probability when I know the symmetric sample space of an experiment. So some examples of that are determining the probability of drawing a specific card from a deck of cards. I know all the outcomes from drawing a card, so I can tell you the probability of drawing like an ace of hearts or something. And again, rolling a dice, or if I know all the outcomes, then I can tell you that in theory what the probability is going to be. Empirical probability is the probability based upon us running an experiment and collecting data. Then we use that data to help us to determine the probability. So for instance, a fisherman wants to determine the probability that they catch a particular type of fish. Well, if we think about trying to do the theoretical probability, we would have to drain the lake and find out all the different fish in the lake, find out how many there are to get that total number. And then we would have to know how many bass are in the lake in order to be able to tell you the actual theoretical probability that you catch a bass. But the fisherman, what he does is, we can't do that. We can't find out all the symmetric sample space. So what the fisherman does is he goes out and just grabs a bunch of net of fish, and he says, look, there are 3 bass in here out of 15. And then he does that again, grabs another net of fish, and it's like there's 2 bass out of another 15. So there were 5 bass out of 30. So then he can say, well, the probability that I'm going to get a bass in the next bucket is 5 out of 30. He uses the data that he's collected to find that probability. And we call that empirical probability. When you're looking at, you ran the experiment and now you're looking at your data to figure out the probability. That's called empirical probability. Another example of that is if a police officer records the number of drivers stopped at a roadblock and the number that tested positive for blood alcohol level over the legal limit. So let's say that 100 drivers came through and 4 of them tested over the legal limit. Then the police officer might say, well, it was 4 out of 100, so it was 4% of the drivers test positive for being over the legal limit. So I think if I randomly choose a driver off the road, the probability that they're driving over the legal limit is 4%. They use the information that they've collected. Now, empirical probability, if you think about when you roll a dice, if you roll a dice 6 times, we would expect, in theory, for one of those to be a 1, one of those to be a 2, one of those to be a 3, one of those to be a 4, one of those to be a 5, and one of those to be a 6. That would be the theoretical probability of rolling a 6-sided die. But you know that in real life it doesn't always happen that way. That you might roll the dice 6 times and get all 6 sixes, or all 6 of them be 1s. Or maybe 3 times it's a 1 and 3 times it's something different. So empirically, it doesn't always match what it should be in theory. But there's this law of large numbers that says if we roll that dice over and over and over and over and over again, a large number of times, that the probability empirically would end up matching the probability in theory. So the more we run the experiment, the larger our numbers are, the closer we get to this theoretical probability. So in cases where I can't come up with the symmetric sample space and I have to run an empirical probability to find out the probability, if I'll collect large numbers of data, then I can get closer and closer to what it should be in theory. So that's what the law of large numbers says, is the greater number of those experimental probability, the closer we get to the true or theoretical probability. So 3 different types of probability we'll look at. Subjective is an educated guess. In theory, what should happen in theory. And then empirical is after we've run an experiment, what is the data we've collected? So with that experiment, what was our empirical probability? Math Made Simple is Simpson Math. Thanks for watching.